Could you give a big applause? Okay, thank you. This is my pleasure to give you the first seminar for nanoscience. So then, like today, I just like give you some presentation of some part of my work. Okay, so I did work on zinc oxide nanorod. Okay, so but this one, just one part. Like today, I'm gonna talk about the effect of surface defect on zinc oxide nanorods to their sensitivity of ammonia gas sensor. Okay, so then before I go to the results, I tell you why I'm interested in zinc oxide. Okay, you know zinc oxide is semiconductor, right?
Yes.
So because it has like really wide band gap, so like 3.37 electron volt at room temperature, and also the exciton binding energy is quite large, like 6 milli-electron volt. Also, it's very easy to synthesize to be nanostructure. Like actually, there are various methods to synthesize nanostructure material. But for this research, we use really simple way to synthesize. You will see later. And also, for zinc oxide, there are a lot of applications. But for today, I will focus on gas sensor applications. Okay, because today we focus on gas sensor application. So then, I talk roughly a little bit about how do they work. For first step, zinc oxide for sure is exposed to air, right? In the air, there are a lot of oxygen gas, and when zinc oxide is exposed to air, oxygen gas is absorbed on the surface of zinc oxide. And what happened? It's gonna deplete the electron from zinc oxide conduction band. You know valence band and conduction band, right? Okay. So it depletes the electron out. And what happened? Then it formed this layer. We call it electron depletion state shock layer. And it leads to the lower in conductivity. Okay. The first step, right? The exposed to air. Then for the second step, it's going to expose to the gas that we want to analyze. But for today, we'll look at ammonia gas. For ammonia gas, when we purge ammonia gas into the system, the zinc oxide with the depletion layer, the ammonia gonna react with the oxygen. Then oxygen release the electron back to the conduction band of zinc oxide. When it releases the electron back to the conduction band of zinc oxide, can you guess what will happen about their conductivity? It's going to be higher or lower? Higher, right? So then, okay, conductivity is higher. So we use this change to observe the sense to the gas, like the change in conductivity higher or lower. Okay. But as you can see from the first slide, from the topic is like we study on the effect of surface defect, right? That defect is going to affect to the conductivity, the electrical property of zinc oxide. So then, before we go into detail, I'll give you a lovely idea. Have you studied about point defect before? Yes, right? So you know vacancy, you know, and like interstitial and site, right? So for example here, for A, this is supposed to, the blue one is zinc, the red one is oxygen. So this is supposed to be zinc atom, right? But it's missing. We call it zinc vacancy. This is the symbol of zinc vacancy. And for B, here, it's supposed to be oxygen, but it's mixing. So we call it oxygen vacancy. Alright? And here, Actually, it should not be anything, right? But zinc here, so we call it interstitial zinc. Something is going between there. Okay, this oxygen interstitial. And here, it's substituted by other thing. This one, it means that some impurity is substituted, right? So these are point defects that it could happen in the structure. And for this defect, it's going to affect for sure to the conductivity. And it can be improved the gas sensitivity later. Okay. Actually, you already know, I already talked about it. The effect of surface defect on gas sensitivity. Why it can affect? Because it can enhance the electron transfer, right? And also it can stabilize the oxygen vacancy. And maybe they provide more active surface, active area that sends to the gas. And then in this work, not just normal zinc oxide. I will tell you how I synthesize zinc oxide nanorod soon. But before that, I modify those zinc oxide nanorod by annealing. Do you know annealing? Annealing is like you put in the furnace, like at high temperature, and purge with some gas. Okay. But in this research, I modify my zinc oxide by anneal in oxygen atmosphere and zinc atmosphere. It's kind of one is oxidative atmosphere, other one is reductive atmosphere. And you see the effect on the gas sensitivity later. But for here, when I anneal in oxygen rich, my hypothesis is like, oh, okay, it should produce zinc vacancy. Okay. And other one, I anneal in zinc vapor environment. Then, okay, my hypothesis is, oh, okay, it should produce oxygen vacancy. Then you see zinc vacancy and oxygen vacancy. Is this true? And how is effect to the gas sensitivity? So, okay, now come to the part of how I synthesize my zinc oxide. It's very common and simple way to synthesize. Actually, you can try later. So just hydrothermal growth, but actually it's like in aqueous solution. So for this, for my starting material, just like use zinc nitrate, hexahydrate, and hexamethylentetratamine, like starting material of zinc oxide. For hexamethylentetratamine, it's like a weak base, right? It just acts as weak base to slowly hydrolyze zinc nitrate to be zinc oxide. But I use equimolar, like very low concentration. So in here, but actually this is in reactor, like closed system. I think in your lab also have this reactor. And then we put in the oven like 90 degrees Celsius for 3 hours. Okay, and the substrate that I use is like sapphire, because the crystal structure is like matching with the zinc oxide. So then I shoot sapphire. Then after that, like I say, after I grow zinc oxide, we call zinc oxide that grows from the hydrothermal as grown zinc oxide. After that, I modify the surface by annealing at 650 degrees Celsius in the tube furnace. Okay, and purge oxygen gas and zinc vapor. Then I get another 2 samples, oxygen anneal and zinc anneal. Okay, and then 1 sample I did hydrogen plasma, and then I will tell you why I did it. Okay, these are the zinc oxide nanorods that I synthesized. So as you can see, this is like a nanorod, right? It's hexagonal. If you look closely, it is hexagonal nanorod. The diameter of This one is around like 55 nanometer. So just like put in the solution, then you get this one. Zinc oxide nanorod. Okay, and here is like XRD pattern. So these pattern of our sample, they are not that different, right? They're the same. It proved that what did I get? I get the word side hexagonal lattice. But actually it matched with the morphology that I shown you by SEM image, right? It's hexagonal nanorod. So, and from XRD you get it's hexagonal, word side hexagonal lattice. Okay, but I want to prove that what type of defect in my sample, right? But the technique that I use to characterize it is cathodoluminescence. Okay, before I go to the result, I give you some background knowledge about the recombination process, how it illuminates with different color. Okay, so actually, as you can see, this is radiative recombination mechanism. There are 6 mechanisms that it can be. Like at first, we bombard the electron beam to the sample, and then the electron from the valence band, it jumps to the conduction band. Then we're going to recombine to the valence band again and emit the light, right? Because luminates. For the first one, it's just band to band. Like for example, for zinc oxide, the band gap is 3.37 electron volt, right? So, okay, it's emit blue light. But then, if our sample have some defect, it can be donor. Those defects can be donor defect or acceptor defect. The light that it emits is going to be different in wavelength. So you can see the different color. So this is donor acceptor pair, or if there are some impurity, they have new level, emit new color. Okay, now you have lovely idea about this mechanism. So then I go to the result of my samples. For the one of ash-borne sample, the black line, it emits the yellow luminescence. Okay, at first I want to say that here, at around 3.37 here, it's proof that this is from band to band of zinc oxide. So every sample have it. But as you can see, for the zinc and nil is like highest, right? It means that maybe like perfect structure of zinc oxide. But here, you can see that the wavelength or the energy is cheap because it has produced some defect in the structure. Okay, we can see for ash-borne sample, it produced yellow luminescence that most of paper that published, they will agree that it comes from lithium impurity or it can be oxygen interstitium. Okay, that is ash-borne sample. But in our sample, from starting material is no lithium, right? Maybe it can be impurity, but I guess it could be oxygen interstitium. But then, after I anneal in oxygen gas, in oxidative atmosphere, what happened? It shifts to red luminescence. Okay, when it shifts to red luminescence, it like the thing that I proposed, like this oxygen gas, it reacts with zinc oxide and produce some zinc vacancy. So now I predict that, I propose that red luminescence comes from zinc vacancy. Okay. So and for zinc anneal sample, this one it shifts to green luminescence. That all well agree that it comes from oxygen vacancy. So from here, like from cathodoluminescent result, like we can conclude that if we modify the surface defect by annealing in different atmosphere, you can produce different type of surface defect. Okay, that one is lower defect concentration, so that why their band-to-band gap is like in high intensity. Okay, but like I say at first that after annealing, I also did plasma. I did hydrogen plasma to the oxygen anneal sample. Why? Because from our result, I think that it should be zinc vacancy. But to prove it, I did hydrogen plasma. Because I believe that if I did hydrogen plasma, hydrogen going to be passivate on the zinc vacancy defect. It's like there are defect, right? And those hydrogen going to be in the place of that vacancy. And if it's true, the red luminescence should disappear, right? Okay, so then I did hydrogen plasma, follow this condition. What happened then? Red luminescence disappear. So it confirmed that, okay, this might be the thing that I propose it should be correct. So as you can see here, the oxygen and the red luminescence here, right? After hydrogen plasma is gone. And also it like the near band edge, because near band edge is like higher intensity. This means that the quality of the crystal is better, like less defect concentration. You already know about the optical properties of my sample, right? Next step, I'm going to show you the electrical properties of those zinc oxide nanorods. For the electrical properties, I did the IV characteristics curve here. I'll show you. For the black one is S1 sample. As you can see, now the current is around just like 3.34 nanoampere at 1 volt. But then, after I anneal in oxygen gas, it improved the electrical conductivity 100 times. So, this means that when we anneal it, not only produce this defect, but it improved the electrical conductivity too. Okay. But the one that I anneal in zinc vapor, the electrical conductivity, it increased around 1,000 times. So quite a lot, right? So now we go to the application part. It's about gas sensor. But how we measure the sensitivity? I explain you how we analyze. So this axis is sensitivity. So it forms the current when we purge ammonia gas divided by the current that generates when just normal airflow. So at first, just normal airflow, I already told you at the introduction that when it adsorbs to oxygen gas adsorb, it depletes the electron, right, and produce the depletion layer. That layer make the conductivity low, right? So it's just here. But then, when I purge ammonia gas in, as you can see, the sensitivity is like higher because those oxygen, it release electron back to the conduction band. Okay, so I purge ammonia for 10 minutes. You can see, electron is released back here, so conductivity is higher. After that, at the second part, I flow air for 10 minutes. When I flow air, again, oxygen is going to deplete electron from the conduction band of zinc oxide. Then the sensitivity or the conductivity is lower, it's decreased. Okay, now you know how to analyze this signal. So now I compare 4 samples. The first one is ascorn sample that produce yellow luminescence. Second one, oxygen anneal, produce red luminescence, zinc anneal, and this one is hydrogen plasma after oxygen anneal. As you can see, 3 of these, like just ascorn and oxygen and zinc anneal, when the concentration of ammonia, this is show the concentration of ammonia from 20 ppm to 100 ppm. When you increase the concentration of ammonia, the sensitivity is higher. It's normal, right? More ammonia, sensitivity is higher. But for the one that we did hydrogen plasma, it happened in the opposite way. But anyway, if you have a look, the sensitivity of the one that we anneal in oxygen gas that produce red luminescence, it gives really high sensitivity, 22.6. It's higher than the ascorn one, around 5 times, and here almost 20 times. Okay, but what happened here? Why it's happened like this? So this is the conclusion. Because it shifts in the position of zinc oxide Fermi level. Do you know Fermi level? Okay, you don't know Fermi level, right? So, but okay, you know conduction band and valence band, right? So, okay, I write down here. This is valence band, conduction band. Fermi level normally is like in the imaginary level. You can't measure it. Okay. So normally it's in the middle of the band gap. But in this case, because we produce some defect on the surface, right, of sample, so then this Fermi level can be shifted up or down, and it affects to the sensitivity. So for here, for the ascorn sample, yellow luminescence, it is oxygen interstitial defect, right? That one is like donor defect. So it shifts the Fermi level up like this. But after we anneal in oxygen gas, it produces zinc vacancy. That is like acceptor defect. So it shifts the Fermi level down. That allows the electron from ammonia to go to the conduction band more. Then it makes the sensitivity of this sample is the highest. But on the other way around, when we did hydrogen plasma, so we destroy that defect level, right? So it shifts the Fermi level up more, because actually everyone agrees that for hydrogen, it's a shallow donor. It's shallow donor, so then it shifts Fermi level up and up. So then it happened in a different way, that electron from conduction band, it flows back to the ammonia gas instead of flow to the conduction band. That's why the signal, the sensitivity signal is happen in the opposite way. Okay. Okay, here can conclude that heat treatment, we can design the defect and the property to our zinc oxide or any other semiconductor. And we found that oxygen anneal zinc oxide nanorod could be a good material for ammonia gas sensor. Okay, thank you for your attention, and if you have any questions, they're all welcome.